Hi everybody, Dr. Pingle here. We're going to talk today about computer-aided design. My aim with this lecture is to give you an overview of kind of a lot of the different issues related to CAD and GIS. We'll talk about a number of technologies, and then the technical aspects we'll kind of offload to their own kind of self-guided tutorial. So these days, people working in GIS, a lot of times, especially at the kind of starting position level, you'll see job advertisements that have a CAD component with them. So CAD is computer-aided design. It's really not that much different than a lot of the things that you're used to. So as a GIS person, you've gotten used to digitizing building footprints or roads and things like that. The fundamental ideas behind CAD are essentially the same thing. We're just sort of creating models of stuff that goes on in the real world. It's particularly useful for CAD to go along with GIS for various kinds of urban planning, kind of architecture, building models, city models, things like that. And that tends to be where sort of the interface comes in. Many local governments and large businesses need people that can track their inventory and their items. And so at sort of the citywide level, a lot of that's done in GIS, but within the building, that tends to be done in CAD. And increasingly, those two kind of universes are merging together. So CAD is still kind of the primary conduit for sort of building level stuff is how GIS people kind of run into it. But then the collection of those building models are kept track of in GIS. We'll talk about this here in a minute, but BIM models or building information modeling is kind of the kind of hot topic in this right now. So we'll take a look and see what that means here in a minute. So CAD has been around a long time. CAD first started to get big when computers started to get common enough and graphics and mice and tools and techniques to sort of rapidly design things in a computer environment. It used to be that people would do these kinds of things by hand, so you would draw blueprints or you would draw design. That was known as drafting. When I was in high school, there was still a drafting class, and CAD was fairly new. What computers enable us to do is sort of do this stuff with a lot more precision and a lot more ease and a lot more replicability than we could do if we were doing it by hand. So skilled draftsmen could produce these things, but this just sort of lowers the bar to making these things accessible. Now CAD really encompasses more than just 2 dimensions. So it used to be you would sort of sketch things up in a way that you sort of see here at right. But these days what we do is we just make 3D models and then we render these sort of 2-dimensional views out. And this has lots of different applications. So there are applications in engineering and architecture and animation. Anybody that's doing sort of 3D modeling is essentially doing things that are CAD-like. And there's a bit of a split between sort of artistic stuff, and we'll talk about Blender and other kind of similar technologies to create video games and movies and things like that, versus sort of engineering, architecture stuff where it's traditional CAD. But the difference between those two is actually not that substantial. So these days CAD is used a lot for mechanical design. It's obviously a lot cheaper to design this stuff digitally than it is to try to make the stuff physically first. Obviously people used to do this by hand, but really the nice thing that you can do with this stuff now is that you can integrate all of these designs. So it's not like you're designing a single component. You're actually designing components that fit together in groups. Those things are dynamic, they can interact. And so you can run tests and simulations and determine tolerances and do stress testing all digitally now. And that's really been kind of a powerful advance, which makes building objects much more reliable than it has been in the past. You can, when you make these kinds of designs, you can create them in all kinds of different ways. 3D printing is something that you've already done, so you can make 3-dimensional objects and you can print those out through this additive technology. But there are also other techniques kind of based on CNC, computer numerical control, and this is where you've got sort of specialized hardware, drills and routers and things like that. We'll take a look at this in a second. That can basically take raw materials and then carve it out into the shape that you've asked for. So the things that do that are CNC machines. They're increasingly very sophisticated. This is kind of a really neat example of one of those things. I'll show you a time lapse of that here in a second. But lots of these kits and smaller machines are now accessible to hobbyists. So you can get these things for just a couple of $100s now. Laser etching tools, drills, saws, routers, all of the stuff is computer controlled in exactly the same way that a 3D printer works. You sort of put in the program, it sort of figures out what it needs to do, the intermediate steps. You basically just hit go and it creates the thing. So you model the digital piece, you supply the raw material, and then the machine just sort of produces a finished result. This is an example of what that looks like. So this is an example of a CNC machine happening at ultra speed, carving out, this is a bicycle chain sprocket. Really, really interesting to watch these things work. Just incredibly precise, quite fast. Obviously this is sped up, but you can see how quickly it's doing things like cutting the teeth and creating sort of a beveled surface. Just immensely powerful approaches and techniques. And these sort of make the development, the research and development side of it go faster. And it makes the one-offs much more accessible and much more easy to price, because you don't need a specialized machine anymore. You don't need to keep things in stock. If one of these things is demanded, you can just sort of create one. So beneficial for a lot of reasons. At sort of the macro scale, the big use of CAD is for modeling entire buildings. So here we're not just modeling little components or rooms, but the entire structure, and not just the physical structure, but the various systems that interact with it. So the electrical system, the heating and cooling system, and so on, all modeled and attached to this one kind of intelligent model that has, it's not just a physical structure, it's dynamic and interactive. They use these things a lot, so there's a term called 4D BIM. They sort of refer to the process of creating buildings. So you can model these things coming into being over time. And it just allows for greater communication and specificity between the architects and the builders, planners and maintenance people. All of these things are sort of now interrelated in the building information modeling.
These days, a growing number of architects, engineers, and contractors are using BIM. And here's why. Global trends are making AEC projects more complex, while advances in technology are helping industry professionals work more efficiently and effectively. This is where BIM comes in. BIM is an intelligent model-based process that connects AEC professionals so they can more efficiently design, build, and operate buildings and infrastructure through BIM, or Building Information Modeling. With BIM, designers create digital 3D models that include data associated with physical and functional characteristics. The power of BIM is how it allows architects, engineers, and contractors to collaborate on coordinated models, giving everyone better insight into how their work fits into the overall project, ultimately helping them to work more efficiently. The data in a model defines the design elements and establishes behavior and relationships between model components. So when an element in a model is changed, every view is updated, with the new change appearing in section, elevation, and sheet views. You can use the information in the model to improve your design before it's built. Gain faster buy-in and approvals with realistic visualizations. Convey design intent to the field. And, most importantly, retain model intelligence from concept to construction. BIM provides insight into a design's constructability, improving the efficiency and effectiveness of the construction phase, and also providing a better understanding of the building's future operations and maintenance. Owners can use BIM for predictive maintenance, asset tracking, and facilities management, and for future renovation or deconstruction projects. When you work with BIM, you'll experience reduced project risk, improved timelines and cost savings, and better project outcomes. And the power of BIM is growing with cloud-connected technologies that let project teams design and work together in all new ways. Driven by global trends, the AEC industry is in a time of transformation. Businesses that want to win more work, deliver projects more efficiently, and design better buildings need a powerful solution. And that solution is BIM.
So CAD data formats are actually a lot like GIS vector data. So you're used to working with points and lines and polygons, and essentially this is what happens within a CAD data model. All of these things, surfaces kind of go together to form these kind of larger components, but everything is sort of modeled on this sort of vertices and surfaces and topology, as well as attribute information model. And this is one of the reasons why GIS and CAD go together so well. They actually model things in almost exactly the same way. They're just sort of dealing with things at a fundamentally a different kind of a spatial level, and often different levels of precision. So when we digitize a building footprint, for instance, we typically don't do that within the specs that are required for a CAD model, which need to be absolutely precise. If we get somewhere nearby within centimeters, we're doing well. The CAD models have to be much more precise. On the other hand, a lot of the things that we do are georeferenced, and CAD models are not. And so it's sort of a different perspective and different philosophy, but the methodology actually goes together pretty well. There are lots of kind of common CAD extensions. So DXF is one of the most popular. This is an Autodesk format, slight misspelling there. STEP is another common one, so the standard for exchange of product model data. There's a version of these kinds of 3D models called Digital Asset Exchange that tends to be more on kind of the artistic side, but is also used for some aspects of CAD, abbreviated DAE, which is often paired with Google KML to be viewable in things like Google Earth. A lot of the 3D formats that we saw with 3D printing actually work just fine in CAD, so STLs and OBJs work just fine. And then CityGML is sort of a larger version of this. If CAD and BIM sort of works at the building level, CityGML is kind of designed to put those things together at just kind of a slightly larger scale. There are lots of different kinds of CAD software out there. So Autodesk is probably the biggest. So AutoCAD, Fusion 360 is the one that I use pretty often. People that are working with BIMs will use a program called Revit. SolidWorks is also probably just about equally as popular. There's a version of a simple kind of CAD program called SketchUp that was originally developed kind of by a startup that was bought by Google and then sold to Trimble about 10 years ago. That program is still a little useful. And then there are various other kinds of free and open source CAD software. Tinkercad is actually made by Autodesk. FreeCAD is an entirely free one. And there's lots of these out there. If you've got open source CAD programs that you've heard of or are interested in, please let me know. So we've mentioned a little bit. CityGML is it's a specification for how to build larger scale, sort of city scale, three-dimensional models where lots of these different parts are integrated. Again, there's semantic content. It's not just sort of modeling the shapes, but those things have meaning. They're interrelated. You can interact with them. Use cases, CityGML will divide these up into 5 different kinds of groups for archiving, for visualization, for navigation, for simulation, and for analysis. All of these should be supported by the model. So again, they're not just sort of representation. They're not just sort of physical representations of the physical space, but again, how those parts combine. CityGML kind of reached its peak, I would say, 8 years ago or so with the CityGML2 specification. The CityGML3 specification is due out soon. I think it kind of remains to be seen whether this is going to take off or not. Many of these kind of virtual reality three-dimensional technologies have sort of sputtered. They gain a little traction for a little while and then kind of they fall apart. So I think what the form that this kind of takes is kind of open at this point. One of the nice things about CityGML is it's sponsored by, or it's developed by OGC, which is the Open Geospatial Consortium. We've seen kind of their hands behind the scenes in a couple of the technologies we've looked at so far. They're sort of the main alternative to sort of the proprietary development of these technologies. And on the CAD side, Autodesk has been one of the major players in this. On the GIS side, of course, Esri is kind of the major player. But OGC attempts to sort of anticipate some of these things and develop standards so that the open source community sort of has a scaffolding that they can rest on as they sort of try to develop alternatives to proprietary technologies. I think the easiest way to demonstrate this is by showing what some of these things look like. So this is a YouTube video of a recent CityGML3 entry as they were developing the specification. So you can see that we're using lots of different pieces of these. We've got sort of solid models that are based on meshes, as we've talked about with 3D printing. We've got point clouds. You'll see that we've got additional sort of means of interaction here on top of that. All right, so here we're looking at extrusion, where we're taking sort of footprint models of buildings and bringing those up. On top of that is a solar irradiance feasibility study. When we click on some of these solid models, we've got additional information associated with those models. We can bring up things like transport layers and so on. So this looks a lot like some of the stuff we've seen sort of in on the Esri side. So let's take a look at that. One of the things that I've tried to emphasize here is the need for semantic content. So that semantic essentially means meaning associated with these things. Again, we don't want these things to just be models of the physical form. What we want is them to have roles and attributes and interconnections. And so that's really what a lot of this stuff is all about, especially at sort of the city level or urban level. For many of the things you might be doing on the simple things you might be doing on the CAD side, that might be less true. But that's the goal, is that sort of you've got something like a BIM where you're not just modeling the parts, but those parts have meaning and they can actually work. You can actually use them to simulate or provide information about things in real time. As I said, Esri has definitely thrown its hat into this ring. Esri supports CAD in a number of different ways. So one of the things that they do is they create a plugin for Autodesk so that you can bring GIS content into that. Again, shapefiles are really not that much different than CAD files. They work in exactly the same way. And so translation between those two technologies is not really all that difficult. CAD can similarly be brought into ArcGIS products. There are a number of good story maps for these. So if you, these are all hot linked in the presentations. If you're interested in some of this stuff, it's easy to sort of at least browse these and see what they're all about. So there's a couple of these that I would just mention: ArcGIS for architects, GIS in BIM, and ArcGIS tools for BIM. All of this kind of rests on a relatively new platform in the Esri suite of products called City Engine. So City Engine is essentially sort of the Esri's proprietary format for City GML, built in some degree on top of that technology. OGC doesn't mean that it's not usable by proprietary entities. It's sort of free and out there for people. They want people to use these specifications. So Esri is basically built on top of that. If you're interested in some of this stuff, there are, if you start getting courses in city planning and urban structure, that's where this would tend to come into play. There are a number of good training opportunities for these. So these are just a few of them here that I've highlighted. As students, you have access to a lot of the Esri training for free. So if you have an interest in City Engine, or if you think that CAD is going to be an important part of what you're going to be doing, I would encourage you to kind of go out on your own and look at some of these training modules and see what you can do. A lot of what happens at that level rests on a couple of relatively easy to understand technologies. One is the building footprint. So a lot of city models are built on sort of extracting either manually or from satellite photos the outline of a building. And in some cases, you'll start modeling things in a little bit more depth and have different roof levels, and they can have slants and more exciting things like that. But at the beginning of this is really just the footprint extraction. If you haven't seen this, this is something you should definitely check out. So I provided a hot link for you here. This is a New York Times article that came out in 2018. Showcasing one of Microsoft's new technologies, not technologies, but initiatives, research initiatives, building footprint extraction. So the goal of this was to be able to take imagery that Microsoft owned and use that as the foundation from which to extract buildings. This is a rather tricky computer vision problem. Microsoft has contributed in a number of really important ways to computer vision problems and photogrammetry. In fact, some of the early photogrammetry was built on a platform called Bundler that would essentially, and in turn, a thing called photosynth that would essentially take all your photographs and turn them into a 3D point cloud. Things like Pix4D and Agisoft and other things like this are largely built on top of some of those kinds of initiatives. They came out almost 15 years ago now. So long story short, Microsoft has contributed quite a bit to artificial intelligence and computer vision, and this is kind of one of my favorite products that they put out pretty recently. All of these buildings are available in GeoJSON format, and you can download them. So you can download the whole, they're all distributed state by state. I'll show you an example of that here in a second. But all distributed on GitHub, really easy to access. You can just download whatever you want. And then GeoJSONs are pretty easily converted to, if you're interested in shapefiles, you can do that. Microsoft or Esri has tools that you can use to convert from GeoJSONs to geodatabases or shapefiles or feature classes in general. But you can also, if you have bad luck with that, my advice is to check out QGIS. Some of those converters work a little bit better. This is what a couple of highlights from the GitHub page talking about how it's done. Again, this is really interesting, just research in terms of how this is done, and Microsoft has contributed greatly to figuring out how this stuff works. And so they have a really interesting model that they use to figure this out. Even the sort of secondary application of how do you polygonize, even if you do extract pixels from imagery that you think are buildings, the next step is to kind of turn that into a vector-based model, and that's not a cakewalk either. And so they've really done a really good work here. At the bottom, there's an example of what the distribution looks like. Again, these are all distributed in GeoJSON. There's an Esri vector tile that you can download to take a look at this stuff if you just want to see it, but you can actually download the original data if you want. These things are getting updated all the time. So this is a multi-year initiative, and so it's not like they just put this stuff out in 2018 and they're done. They're kind of continually going back, and if you follow this project on GitHub, you can see kind of the number of updates that come down monthly, at least several, a handful, a dozen or so every month. If you are, I think we pointed this out in one of the previous lectures, but just to kind of tie things together, if you're in Virginia, there are building footprint polygons that are also published by VGen every quarter. So these tend to be a little bit better if you're looking for nationwide data. I don't think that there is a better data set than the Microsoft building footprint data set, but we're lucky in Virginia that there's an initiative to do that here. One of the older initiatives that I at least want to mention is the collaboration, sort of the initiative that was led by Google Earth. So building models have been incorporated in Google Earth for at least 15 years. They really kind of took the lead on a lot of the stuff. And at the time, this was done kind of in a couple of different ways. Now, a lot of that stuff is just sort of done in an automated way by computers. So if you look at Google Earth now and you turn on the building layers, what you're seeing there is sort of this AI construction of these things. But 15 years ago, this was actually done. A lot of the models that were in there were hand completed. So they would use a program called SketchUp often to create the buildings, and to you could take photographs and sort of put those photographs on the faces of them. So they look very realistic. And so that technology is still kind of worth keeping an eye on. Google Earth's models are not semantic, so they do tend to just be sort of shells without a lot of content associated with them. But the shells are very good, and so if you're interested in sort of cutting edge visualizations of buildings, I would encourage you, if you haven't looked at Google Earth in quite some time, check it out again. There have been some really significant improvements in how buildings and trees and urban landscapes look. They just look a lot better than they did even 5 years ago. When we talk about the virtual reality section, that too has some really interesting pieces. It's important to mention, and I think I did this towards the beginning, that 3D modeling isn't just really all about architecture or engineering. So CAD is really just sort of one side of sort of the 3D modeling coin. The other side is kind of pushed forward by game designers and artists who use programs like Blender to create scenes and models. They're also interactive. They can also have semantic content. Lots of really interesting stuff. If you haven't checked out Blender and you're interested in this kind of modeling, I would encourage you to give it a try. It's free, it's interesting, and as I'll show you here in a second, there's a lot of really interesting geographic content that you can create with it. So I'm not going to play this video, but if you're interested, and I know that a couple of students in the class are, there are a number of great tutorials for how to use Blender to create some sort of some photorealistic scenes. This is just one of them. If you Google GIS and Blender, you'll see hundreds of videos out there that talk about those two things put together. It's not something that I do very often, but the look and the texture and the feel of these things tends to be really good. And so if you have an interest in that, definitely that's worth pursuing. One of the really important tools in that toolkit is the Blender GIS add-on that can sort of help put some of these things together. That's a big world, and again, if you have an interest in that, I definitely encourage you to explore that. One of my favorite applications of that is the incorporation of things like OpenStreetMap data. So we haven't talked a lot about OpenStreetMap, but OpenStreetMap is a sort of public repository, kind of like a wiki, where people can add buildings and roads and bus lines and all kinds of interesting things. And that's been around for almost 20 years now. It's a very complete data set. It's really easy to get sort of all of the GIS data that you would need to represent a city. And so there are some really good tutorials out there for how you can sort of quickly spin up a model of a city using OpenStreetMap data. And this is kind of one of these areas where open source has really done a very good job. Again, it's the semantic interrelated content might be a little bit weaker, but OSM often has a lot of attribute tags, so it isn't like you're just getting a physical model. There really is a lot of stuff with that. So I wanted to talk about just a couple of technologies to actually do CAD. So we've talked about CAD and systems and kind of a lot of interrelated technologies. How do you actually get started doing it? Well, I got started with a program called SketchUp. So SketchUp at the time was kind of a really big groundbreaking software. It really was easy to use, incredibly easy to use, much easier to get started than a lot of its competitors. It was initially kind of created by a startup. That startup was very quickly bought up by Google. Google saw the potential of this to incorporate into things like Google Earth. And again, that's where a lot of these initial building models came from. Google kept it for a while and then sold it. So they sold it to Trimble about 10 years ago. So Trimble is a company that we know oftentimes associated with GPS units, but it's really kind of evolved into a big geospatial organization. They do all kinds of different work. But one of the things that they did was they bought SketchUp and now they're the distributors of it. So you can do a number of things with that. You can model anything from sort of small tabletop items to modeling rooms, to modeling buildings, to modeling landscapes, lots of different things that you can do with this. I've used it primarily for a lot of kind of smaller pieces, modeled sort of different rooms with it. When I first got into 3D printing, I started using SketchUp to sort of make the products. I designed a drone, a flyable drone, and did all of the design in SketchUp. So it's really quite powerful and good software. Unfortunately, I would say that the model of distribution is changing. So they're trying to sort of, I think, figure out better ways to monetize it. For a long time, it was free. It's still kind of free for educators. It's becoming increasingly difficult to use without a lot of strings attached. So while I still like this software and still use it once in a while, I've kind of adopted another technology as my new favorite. But if you want this, you can actually access some of these tools, which I'll show you here in a second, over the cloud. So it's now incorporated as part of the G Suite series of software. It does not seem to be enabled for Virginia Tech at the moment, and I'm not sure why. But I don't use the cloud version anyway. I tend to use a version called SketchUp Make, which you can still find a copy of and is still legal to use. But it hasn't been updated since 2017, and they're sort of trying to phase that out in favor of paid software distributed as SketchUp Pro. One of the pieces that's attached to this is the 3D warehouse. So these are a bunch of SketchUp models that people have made and uploaded into an archive. Lots of really interesting things on here. All of those can be browsed sort of independently just from the web, or you can bring these in to SketchUp. This is an example of just a quick SketchUp project. So you can essentially draw a box, you sort of extrude it up. You can draw all kinds of shapes. So there are circles here. I'm drawing an arc on the side of the box, and then using this what's called a push-pull tool, which is kind of like an extruder to sort of bring that out. And you can do the same thing to create holes. And you can, I guess I'm covering up here, but you can actually type in dimensions, so it's not just all done willy-nilly by hand. You can type in specific values that you want to be very precise about how you're modeling these things. So Incredibly easy software to sort of start making 3D shapes. As I said, SketchUp is free for schools to use. So you should have access to this. Unfortunately, as I was testing it out, it wasn't working. I can't necessarily advise you to do this, but if you're interested in kind of poking around, SketchUp again is distributed as SketchUp Make, which is a downloadable, installable application like anything else, or you should be able to interact with this stuff via the web. So I said that I've more or less stopped using SketchUp at this point in favor of this, which is Autodesk Fusion 360. So this is a cloud-based way of doing CAD work. It's really, really fairly intuitive, especially if you follow along a couple of these tutorials. Again, it's free for private use for, I think, a year. It's free for students and educators to use. So this is kind of my recommendation for where to start if you're interested in learning some CAD. This is an example of doing similar things that I just did in SketchUp using the CAD software. Just sort of first thing, making a box, picking a plane, drawing the bottom of the box, and then extruding that up. You can again type in specifications here, and one of the nice things about CAD, or at least Autodesk Fusion 360, is that the models are what are called parameterized, so it's easy to kind of go back and change things down the road. You don't have to recreate the whole model. You can define what are called constraints that sort of keep things all put together. Really powerful technology. Here I've drawn a circle and I'm just sort of extruding that out again. Not too much different than what I did for SketchUp. One of the nice features here is that you can draw things like, you can make threaded holes. You don't have to model those. Those are all sort of incorporated into the technology. So you can draw a hole, you can have it go through the system, and then all you need to do is add threads. So there's a threads button. You click on the hole that you want to thread, and it'll do it for you, and you have all these different profiles that you can choose from. Really interesting stuff here. I've found it to be very intuitive, very powerful. And then finally, one of the last things that you can do, if you're using this in sort of CAD software, you probably want to export it in that format. I'll often be using things that I want to 3D print. So essentially, all you have to do is right-click, hit Save as STL, and hit OK, and you can save that file out and then throw it right on your 3D printer. So I've been using this for a few months now. Really like it a lot. And so that's kind of why I wanted to bring it to your attention. SketchUp is how I got started. I think it's still pretty good. But if I were starting from scratch, I would start with Autodesk Fusion 360. Virginia Tech has sort of an in-house representative. So Bradley Turner teaches classes sort of organized through the library. If you are interested in doing this stuff, I would recommend emailing him. Tell him that you're interested. I took one of the classes with him, and he was a great instructor. So nice to have an in-house. So he's Virginia Tech's sort of in-house Fusion 360 ambassador, and his whole job as an Autodesk student engagement ambassador is to kind of help you learn the stuff and kind of teach people the greatness of Autodesk Fusion 360. Autodesk Fusion 360 is free for educators and students. As I said, this is the URL to get started. If you just Google Autodesk Fusion 360 student download, you'll probably land right on this page. The download is pretty simple and painless. It went pretty smoothly for me. There are also a lot of good tutorials online. These are just a couple of them. What I'm going to have you guys do is just sort of give you an opportunity to explore some of these things on your own. And then, of course, YouTube is your friend. Plenty of Autodesk Fusion 360 tutorials, little bits if you've got a particular question. There are web forums that you can go to. So oftentimes, I've got enough to sort of get the general idea, but it doesn't take too long before it hits something and I know kind of what I want to do, but not sure how to do it. I can go on the forums and sort of figure it out from there. So there's a lot of trial and error to figuring this stuff out, but it's nice to have all of these resources to back it up. One of the fun technologies that Autodesk puts out there is Tinkercad. I haven't used this myself, but as I was prepping the lecture, I saw this. What you can do is sort of put a 3D model in there, and it will sort of tell you how to make that with Legos or other sort of brick models. Sounds like fun to me. So we're going to wrap things up there. I wanted to thank you for your attention. This is just your first sort of step into CAD. I'm by no means a CAD expert, but I've been doing little bits of it for a long time. If I can't answer your question, probably I can point you in the right direction. So with that, we'll wrap things up. Thanks for listening, and we'll see you next time.